last time we met, we talked about zeros and multiplicity of those zeros. I forget exactly what the equation was that we were working with because I made that one up on the spot. So I'm going to give you a very similar equation. Whether it's f of x, g of x, h of x, or y equals, doesn't matter. We're going to say that this one is 5x times x plus 3 to the second power times x minus 4 to the fifth power. And we talked about the zeros, the x values that would make this function equal to 0. And we said that one of them was an x value of 0, an x value of -3, and here we have also an x value of +4. 0 being plugged into here would cause the entire expression to equal 0. A -3 getting plugged in here or a +4 getting plugged in here causes the entire thing to equal 0. The multiplicity of these zeros the first one has a multiplicity of 1, -3 has a multiplicity of 2, and the x value of 4 has a multiplicity of 5, and those are coming from the exponents. There's an invisible exponent of 1 there. This 2 is coming from this exponent, and the 5 is coming from here, in case that wasn't obvious. And now what we're going to do is use end behavior and the zeros and their multiplicity in order to draw a graph of this function. And let's give ourselves an axis system over here. The lowest x value that we're going to be looking at is -3. 1, 2, 3. Largest x value is +4. And we do need a little bit of space to spread out on either side of those. The x value of 0 as a 0 is going to occur at the origin. That's where x equals 0. So in other words, we're talking about 0, 0. We also have -3, 0. -3 is the x value, y is the outcoming 0 value, and the x value of 4 is also a 0. These zeros also cause us to have, as you're seeing on the graph, these are x-intercepts. Now the degree of the entire polynomial can be found by adding the multiplicities. If we were to take this entire polynomial and multiply it out, we would have an x to the first power times, eventually we would have an x squared, eventually we would have an x to the 5 after multiplying that out, and x to the 1 times x to the 2 times x to the 5. We know that the product rule for exponents tells us that this would equal x to the 1 plus 2 plus 5 makes 8. So I'm going to put a total of 8 down here. Now if you wanted to write down the stuff that I had in red up there, you could. I erased it just to get rid of the clutter from my notes, but you can keep it. The important part is that we ended up with a total degree of the polynomial being 8. Why is that important? It's important because that means that the degree of our polynomial is even. And the other important aspect of the actual equation for the polynomial is that the leading coefficient is 5, which is positive. And that's these two things along with the zeros are going to allow us to draw our graph. with an even degree exponent with a positive leading coefficient. If you look back in your notes at end behavior, you will see that that means this thing is going to be rising left and rising right. The multiplicity of this 0 up here, this multiplicity is odd, which means that our graph is going to cross the x-axis at that 0, or at that x-intercept. This one, this multiplicity is even, which means that the graph is going to come down to that 0, touch and turn back. Touch and back. And this one is odd again, so our graph's going to cross there. And of course, I'm going to show you what I mean by all of this. So let's get to it. I'm going to look at the x value of -3 first. I'm going to work from left to right with these x values. So let's look at the x value of -3. We're supposed to be touching and turning back. Touch and turn back means our graph's going to come down, touch at the x-axis, and then turn back. So it started on the top side of the x-axis, so it's going to stay on the top side of the x-axis. It's going to stay positive. Now, at the next 0, which is an x value of 0, we're supposed to be crossing. So our curve needs to come down to this 0, cross the x-axis, and at our x value of 4, we are also supposed to be crossing. There's the cross that's happening on our way up, and you can see that we've done it correctly because we are still rising left and rising right as we were supposed to, according to our previous conversation about end behavior. All right, so that is the use of our conversation about end behavior, even degreed polynomial, positive leading coefficient, and the utilization of our zeros, and the utilization of multiplicity, where odd multiplicity tells us that we cross at that particular 0, even multiplicity tells us that we touch and turn back. So a lot of little components. You're going to want to practice some of these to make sure that it goes smoothly for your next exam. Let's move into our next subtopic, which is the intermediate value theorem. The intermediate value theorem is much simpler than what we were just talking about. It has considerably fewer components, and let's talk about it sort of in generality. And I'd like to say that if our function g of x is a polynomial, and that's important because, as we talked about in class, I believe in both of my sections of college algebra, we talked about how polynomials are smooth, and most importantly here, they're continuous. So there won't be any breaks in this nice curve, or nice smooth curve that we're looking at, just like we saw in the previous example. The curve didn't come down and then have some kind of a gap in it and then restart down here or anything like that. So it is important that we're working with a polynomial. And just imagine you don't have to actually imagine it because I'm going to draw it for you, but in this somewhat generalized conversation, let's assume that we're working with our function g of x and that g of 2 is equal to -3, and that g of 7 is equal to +5. What the intermediate value theorem tells us is this: g of some number is going to equal 0. This number will be between 2, and 7. Let me illustrate this for you, because so far what you're doing is listening and jotting down your own notes. Let me show you what this looks like. X values of 1, 2, 3, 4, 5, 6, 7. Y values are going up to 5, 2, 3, 4, 5, down to negative 3, 3. And I'm going to actually plot these 2 points. So I'm going over 2 and down 3. There's my first point. Next point is at 7, 5, over 7, up 5. Great. This is a polynomial, which means that the graph, I have no idea what the graph looks like, right? Because I didn't actually give you an equation for this thing, but we can see that the graph is passing through those 2 points. And what you'll also notice is that in order to get from below the x-axis to above the x-axis, we had to cross the x-axis. And that crossing is happening at a point that has some x value, and at that point the y value is 0. So it works. The intermediate value theorem is true. If we're starting out at a point that's below the x-axis, let's grab a different color. If we're starting out at a point that's below the x-axis and we're progressing to a point that's above the x-axis, then at some point in time we must have crossed the x-axis. And at a point where we're crossing the x-axis, we have a y value of 0. All right, that's a lot of scribble on there. Let's get rid of all that. Okay, let's try a problem that looks something like something you might see on our next exam or in a homework assignment. For example, the phrasing might be a little bit different, but does f of x equal x to the 4th plus x to the 3rd minus 2x squared plus 6x have a 0 between negative 2 and negative 3. Now remember, excuse me, these are both x values. These are the equivalent to these x values. So we now need to look at the corresponding y values. We're going to have to calculate those, and then we'll see. If one of the y values is below the x-axis and one of the y values is above the x-axis, then at some point in time, we must have crossed the x-axis. All right, so this is a little bit time consuming, but we're going to have to evaluate f of negative 2. So let's go through the motions here. We've got negative 2 to the 4th power plus negative 2, and notice I'm using my parentheses, especially when we're plugging in a negative value. That's going to be helpful. And if you were to type this into a calculator, you would really need to use the parentheses, because that's going to help the calculator apply the order of operations correctly. PEMDAS. Negative 2 to the 4th power is positive 16, because we've got a negative number to an even exponent. Here I'm adding negative 2 to the 3rd power is equal to negative 8, so that's going to be, this is equivalent to subtracting 8, so 16 minus 8. We've got minus 2 times, this turns out to be positive 4. And then we're adding a negative 12. Let's go ahead and put it in that way, plus negative 12. And then if you wanted to, you could rewrite this as 16 minus 8 minus 8 minus 12. And obviously that is equal to negative 12. So our first point that we're working with here started with an x value of positive 2, finishing with a y value of negative 12. So let's write down those coordinates, -2, -12. Great. We're going to go through that process one more time with the x value of -3, and then we'll be able to make our decision about whether or not we have a 0. In other words, whether or not the graph would cross the x-axis with an x-coordinate that's between -3 and -2. To the third power minus 2 times -3 squared plus 6 times -3. All right, -3 to the fourth power is positive 81. This turns out to be adding a -27, so I'm going to write it as -27. This is 9 times -2 makes -18, so I will write -18. And here's another -18. This is 2 nines. This is also 2 nines. This is 3 nines. That's a total of 3, 5, 7 nines. This is 9 nines. 9 nines minus 7 nines equals 2 nines, which is positive 18. So you could do all of that in a calculator, of course, or with some long subtraction if you're just doing it with paper and pencil. Ultimately, we come out with positive 18, which means we have coordinates -3, positive 18. And what we see now is that we're starting, let's draw a quick graph. I don't like that one. Let's do that again. -1, 2, 3. At -3, we're way up here at 18. At -2, we're down here at -12. -3, 18. -2, 12. It's a polynomial, so it's continuous, which means somewhere between x values of -3 and -2, we do have a 0. I don't know what the x-coordinate of that 0 is, but I know that the y value is 0, and all we're trying to do is determine whether or not there is some x value that would cause a y value of 0, where that x value is between -2 and -3. And the answer to that question, in this case, is yes. All right, on to our very last tiny little topic. This one's even easier than that conversation. It refers to turning points. And if you will just write down this one sentence, and then I'm going to show you an illustration. If our function, let's call it h of x, doesn't matter what it's called, is degree n, in other words, the largest exponent is n, then it has, at most, which is not language that we hear very often, at most, n minus 1 turning points. A turning point is where we go from increasing, it's not much of a G, there we go, to decreasing, or from decreasing to increasing. And I'm going to show you what I mean right now. There we go. So now we're in Desmos, desmos.com. And so we're up here. That is y equals x to the fourth. It's a fourth degree polynomial. And our function, our graph, is decreasing on its way from left to right. If we were walking, we'd be going downhill. And then we'd hit this little flat spot, which actually only happens at an instant there, and then we would have to start walking uphill again. So this is the turning point. Very exciting. Delete. Now let's turn on our second graph. By comparison, it's got a totally different shape, well, pretty different shape. What you're seeing, the similarity in terms of end behavior, however, ugh, I keep screenshotting.
I didn't get that.
I'm gonna give you something. There we go. So obviously the shape is pretty different, but one of the similarities that you're seeing is it's still rising to the left and rising to the right, both of these, because both of these equations have positive leading coefficients and even degree. They're both degree 4, both positive leading coefficients. Okay, but I'm not seeing any additional turning points. I've still only got one turning point on my second graph. I only had one turning point on my first graph. Let's see if we can get something different by turning on our third graph. Yes. The primary difference between the equations, which you won't have to be able to anticipate, is I introduced this third degree term. So there is an x to the third in that equation. The polynomial as a whole is still degree 4 because of the x to the fourth in front of it. But it turns out that adding in that x to the third caused us to have not just one, not just two, but 3 turning points. You can see we're going downhill, changing to uphill, and then I'm going from uphill to downhill, and then yet again another change where we're going from downhill to uphill. So that's how we're determining those turning points. So again, 4th degree polynomial, that's our n value. 4 minus 1 equals 3. That is n minus 1. So we have at most n minus 1 turning points. And that is the end of the section. Thank you so much for taking the time to watch this video and pick up the last part of the content from the section that we didn't get to finish up in class. Now it's time for homework, and I will see you on Tuesday. Thanks so much.